So now we're going to talk about forces in fluids. And during this whole course, we're going to kind of be talking about different vocabulary terms. So I'm going to have those listed here on the side of the board. Those would be really good to know and be able to define at any point, and you'll be really quick at answering these kinds of questions. So the first thing, for forces in fluids, we had to talk about pressure. And what pressure is, in equation format, it's just a force divided by an area. Now if we wanted to kind of conceptualize what this means, it's whenever we have something that's applied, let's say both of my feet, for example, put on the floor, we have a force that's being put over a certain specific area. Now that's the pressure that I'm exerting on the floor. So let's think about what would happen if I was to take one of my feet off. What would happen to the force? Am I exerting a greater or smaller force on the floor? And what would happen to the pressure? Is the pressure greater or smaller? So considering the fact that my weight didn't change, the only thing that did change is the area, my force didn't change at all. But the pressure, it did change because I have a smaller area now that I'm dividing into the force. So that's why, for example, let's say we have an elephant that's standing on the ground. He can exert a pretty good force, but he's not going to exert that much pressure on the floor. Versus if we had a ballerina, I can't exactly do it right now, but if we had a ballerina that was standing on her tiptoes, she would actually be exerting more pressure on the ground than what the elephant would. So now knowing what pressure is, we can go ahead and start talking about how that applies to fluids. In a fluid, what happens, and here I'll go ahead and draw our fluid. We'll say this is a tub full of water. There's a few postulates that you need to know about the forces in fluids. First off, whenever you have pressure, that's whenever you have things that are pushing on all sides of you, and the deeper that you go in your fluid, the greater that pressure is going to be. So if I am floating, let's say this is me right here. Well, I guess I'm not really floating. But if I'm in the water right here, I have a certain force that's exerted on me, and I have a certain area that's going to give me a certain pressure. And if I was to dive down a little bit deeper, I have a greater pressure that's exerted on me simply because I went deeper. Now you guys have probably experienced this whenever you're swimming in your swimming pools. Whenever you dive down to the bottom, you feel a whole lot of pressure in your ears. It feels like your eardrums are about to pop. So that happens just because you're going deeper. And if you think about it, it's because you have more water above you that can be pushing down on you. Okay? Now another thing to know about pressure, whenever you're in water, it's going to be the same for a single point in all directions. So if this is our point, we're going to have a pressure, let's say, of this magnitude on all sides. We're just representing that quickly with arrows. So if I was to combine the ideas that we've already talked about, let's take that point and move him deeper. If we move him deeper, he's still going to have pressure on all sides, but his pressure is going to be greater. So we could say he has pressure of this magnitude now. Okay. So here's another thing. Let's say we had something larger than just a little point. By these points, I'm talking about like no area, no radius or anything, just a point. But if we have something larger, let me draw another tub. If we had something larger like a beach ball or a balloon, what have you, notice this single object, it covers several different points. So if we're talking about the pressure at the very top, he's going to have about the same as maybe this point, right? But if we're talking about the pressure at the very bottom of this beach ball, it's going to be greater because he is deeper. Even though it's the same object, it's a different point or a different depth in the fluid. So we could probably equate that to about this. And if you notice, the pressure should, well, let me make this a little bit better. The pressure should be decreasing as you go up on this object. Now, whenever you're thinking about why things would move, you have a greater pressure at the bottom than you do at the top. That could potentially be one explanation for why things float. So we've already talked about what pressure is and also how it applies in fluids. The other thing I wanted to talk about is pretty important. It's buoyancy. It's Archimedes' principle. Okay, so we just talked about pressure a little bit, and now I kind of want to apply a little bit more about what causes things to float whenever you're in water. So pressure, we know it's the force divided by area. We know how that can explain why things would float. There's another thing I wanted to talk about. It's Archimedes' principle. It has to do with buoyancy. Now what buoyancy is, it's the weight of the fluid that's displaced by the object that you place in the fluid. So that sounds like a little bit much. What it is basically is if I have a tub, you're going to have some water that's inside, right? And if I was to put, let's say, a balloon inside, that's going to move some of the water away from where that balloon is. So this balloon is taking up the space of X amount of water, okay? Now that water, it's not just going to disappear, it's going to cause this water level to rise. So that water level is going to go up just a little bit. Now if we think about why these things want to float, or if we think about what force is pushing upwards on them, that's just going to be the weight of whatever water would be in the place of the object. So if we had a scale, let's go ahead and take a scale real quick. If we had a scale with a beach ball on it, we'd say it weighs like, I don't know, maybe a pound. And let's take the same amount or same size of fluid that it's displacing and put that on a scale. So we'll say this is our water, okay? That water, we're going to say it's going to weigh like maybe 10 pounds. Now if we're looking at this object, we know it's got a 1 pound downward force that's caused by gravity just from its weight. We also know from this that it's got about a 10 pound upward force because of buoyancy. So that's another word I'm going to write down. It's displaced fluid. Now that's probably somewhere where students get really hung up. They think buoyancy is just something that pushes up on it. It doesn't have anything to do with the weight that the object has though. It only has to do with the weight that the displaced fluid has. So buoyancy isn't the measurement of the difference between these two forces. Buoyancy is strictly the upward force, this bottom arrow, okay? So another thing, let's take an example. Say I had, and let me erase these scales real quick, you get the idea. Say we had a cannonball that was like this big, and say we had a balloon full of air that was this big. Here's our balloon, okay? Now between these two, which would actually have a bigger buoyant force? Now a lot of people are inclined to say the balloon because the balloon's going to float and the cannonball is going to sink. That's actually incorrect. So if you look at these two, you notice the cannonball, even though it's heavier, it's displacing more fluid. So you just look at the volume of the objects to see which one actually has a bigger size, regardless of how big the mass is. Whichever one has the bigger size and is displacing all the fluid, that one's going to have the greater buoyant force. So this one we could say its buoyant force is about that big, while this one only has a buoyant force of maybe that much. Now if we're comparing the weights, or the gravitational force on these guys, we know that the cannonball, that's going to weigh a ton, so we'll give him a big ol' arrow. While the balloon, it weighs next to nothing. So his downward force is going to be itty bitty. So whenever you look at these arrows, even though this one has a greater buoyant force, his gravity overpowers the buoyant force, and that's what's going to cause him to sink. It's not because he doesn't have a buoyant force. The balloon, on the other hand, he weighs like next to nothing. Even though he has a smaller buoyant force than the cannonball, his buoyant force is still greater than his gravitational force, or his weight. So that's why the balloon's going to float. Okay, so with what we just talked about, just to kind of recap, a few words you might want to know. Besides displaced fluid, you have to think about the difference between volume and mass and weight. The things you'd want to remember about them is that buoyancy depends more on volume than anything else. So if in volume, that's just how much space something takes up. So you could have something that's really massive or not massive at all. If they take up the same amount of space, it's going to have the same buoyant force. If something is more massive than another, that doesn't affect buoyancy. All that affects is gravity. Okay? Now mass and weight, we already know how those differ. Mass is something that has to do with what you're composed of. Weight is how much that gravity wants to pull on you. Okay? So just don't get confused. Buoyancy doesn't have to do with any of these two things. Even if gravity is pulling really hard on a very massive object, it's not going to be very big if it doesn't have a very big volume. Versus if something has an enormous volume, and let's say it has a very big mass and weight, it's still going to have a greater buoyant force, even if it wants to sink. So there's a few misconceptions that students usually have. Now another thing I wanted to talk about is what happens when you have something that floats. So say you have a big ball of styrofoam. Now whenever we're talking about the buoyant force and the weight, if we're comparing those two, we know that the buoyant force is going to be greater than its weight. And that's just easy because we know that the water, if the water was in its place when we stuck it on a scale, the water would weigh quite a bit and put that weight upwards. That's the buoyant force. While if we took the actual styrofoam and put that on a scale to weigh it, he wouldn't weigh that much at all. So he would float. Now what happens whenever he does start floating? Whenever he breaks the surface of the water, let's say he's up here, he's going to kind of bob up and down for a little bit and then he's going to stop. He's just going to stay resting on the surface of the water. Now the reason for that, notice as soon as he breaks the surface of the water, he's displacing less water. So even though his volume didn't change, the amount of water that he's pushing out of his way, that's decreasing. So whenever he comes all the way up, the buoyant force, that's actually going to change because the amount of water that is displacing, that's decreasing. So this bottom arrow, that's going to go down as well. Now his weight That's not going to change. Not unless he's changing his mass, but that's not going to happen here. So it's just going to bob up and down while the buoyant force is increasing and decreasing as it moves in and out of the water. And it's going to keep doing that until it finds an equilibrium with its weight. Whenever it finds that, that's whenever it's going to be balanced. That's whenever it's going to stop moving and just be floating on the surface of the water.